All right, well, today we're going to be doing a little different kind of topic. It's on the topic of microgravity. I remember listening about 2 days ago, I think, or yesterday or whatever, somebody was talking about some preconceptions that kids come into the classroom with. And I've got one for you right now to start off with, and I'm going to ask you a question. And I'd like you to answer this question based on what you think your kids would say if I asked the question of them. So you don't have to worry about this is your idea. What do you think they would say if I asked this question of them? All right? Here it goes. And please answer if you think you know the answer to it. What causes astronauts to float in space?
There is no air.
What?
There is no air.
No air. Well, no air. But what did you say?
No gravity.
No gravity. And what else?
There are suits.
There are suits. Okay. What if you had to guess of all those three right there, and there's going to be more, by the way, but if you had to guess of those three answers, which one do you think most of the kids would say would be correct?
There is no gravity.
No gravity. Almost 90%. I've done this question many times, and like 90% of the kids will say no gravity in space. Just about every kid says that, and most adults will say there's no gravity up there. But now let's have a little fun here. I'm going to ask you another question, and what do you think people are going to say to this one? What keeps the moon in orbit around the Earth?
Gravity. Gravitation pull.
Virtually every kid will say, oh, that's gravity. Now think about that for a moment.
So if there's no gravity, how does the gravity keep the moon?
Yeah. And you do get this little conflict, and you can watch it. You have the kids think about it for a bit. You don't tell them, what's going on here, and let them think about it. And pretty soon they begin to. A lot of the kids will start putting together no gravity in orbit, but it turns on again for the moon. How's that happening? So if that happens, if the kid starts to think that way, then you have a doorway opening up to perhaps another explanation. So that's what we're kind of looking for by this particular example right here. You have a chance for another explanation. And I'm sorry to say this, the explanation or the answer is microgravity, which makes no more sense than saying no gravity. Microgravity is kind of weird too, but that's the word they use today to describe all this. And I'm going to explain to you what that means. And it's not a very good term. It's a very poor term. But I'll explain to you what it means, because now if you're going to do scientific research on space station and so forth, you have to be able to use the word microgravity correctly, because everybody uses it, even though everybody hates it. It's kind of hard to see this, but we see these astronauts in here inside a spacecraft called Space Lab. It was actually something carried in the payload bay of the space shuttle. And Space Lab's no longer flying, but what it does is the astronauts simply seem to be floating all through the thing. We all see that. And it's very easy to conclude that the reason they're floating is because there's no gravity. Now, so we ask kids this question, what causes them to float? And I want to point out to you, this is a trick question. More so than just whether there's gravity or not. The other part of the trick question is, what are you floating on? Floating is a buoyancy phenomenon. If you're floating, you've got to have something to float. Are they floating on the air? Why can't you do that down here? That's the problem. Okay, let's talk a little bit about the space environment. And that'll help us to understand what's going on up there. Now, first off, we're going to look at the overall environment, which has a series of factors, natural factors and artificial factors. The natural ones are the things that are always up there. When you get up there, that's what it is. And the artificial ones are the things that you create by being there. Well, the natural factors are things like space vacuum. Okay, no air to breathe. Kids know about that. You can ask kids what's space like, and they're going to say no air to breathe. Yeah, there's no air to breathe. Now, the air problem is more than just suffocating up there. Air rushing out of your lungs. You can't keep it inside. I mean, there's no way to keep it in there. You're not strong enough to do so, because the pressure differential between the inside of your lungs, if you were to step out of the spacecraft, would be 14.7 to 0, and it just is going to come out. But then also you don't have pressure on your body, which means that you are going to begin to expand a bit, because of the moisture will start to boil. Your intercellular moisture, the blood and so forth, will begin to form bubbles. And that will cause you to start to swell a bit. So that's bad. The temperature range up there in the sunlight, well, it's very hot. The kids say hot, cold. Hot part is 150 degrees Celsius in sunlight, and the cold part would be about minus 100 degrees in the shade. So when you're in space, if you are facing the sun, this side is 150 degrees. This side in the shade is minus 100. So you've got a wide temperature range, just even in your own body. That's one of the challenges of a spacesuit when they go out and do spacewalks. You've got to be able to balance that really, really cold with a really, really hot. And it takes a very active cooling system inside the spacesuit to do that. Then you have high-speed particles, which are debris, and could be little micrometeorites and so forth. And you've got electromagnetic radiation, ionizing radiation, we call it, because what it does is it breaks up atoms and knocks off electrons and so forth. It's really bad stuff because it damages your cells. It can damage your DNA. It can trigger all kinds of bad reactions. Now, we haven't had much of that yet, but the radiation has led to a higher than normal incidence of cataracts for astronauts that have flown, especially for long periods of time. So that is a real thing there to be worried about. Then you got your artificial things, like space debris. You dropped a hammer or something, and someday it's going to come back at you at about 17,000 miles an hour. And that's a bad thing to have happen. Secondary radiation. Okay, you get hit with something really big. Now, I'm afraid you can't see that very well, but a ray hit that thing, and then it caused a spraying of smaller particles. It hits the wall of the spacecraft. It sprays smaller particles, and you can actually get more radiation than if you've just been hit by the big one. You can get more hits as a result. So that's a cascading effect.
Are these gamma particles?
What?
Are they gamma particles you're talking
Oh,
about?
we're talking, well, the really big ones, we're talking about the galactic particles, like an iron nuclei.
Okay.
We're talking about big particles. And then the smaller ones are the solar particles, the electrons and protons that are being shot out by the sun. Those are called solar particle events, SPEs, and the other one, then you got the haze, which are high energy particles, are the things coming from outside the solar system, from interstellar space or intergalactic space. Okay. And then finally we have microgravity. And this is something else that is created by our being there rather than it's always there all the time. And you'll have to see how microgravity is created first to understand why I say that. Okay. Of all the natural and artificial factors in the environment of space, microgravity exerts the greatest influence on living things. It really has a big effect on living things. And we spend a lot of their time up in space monitoring the astronauts and conducting experiments, trying to find out what the effect of this is on their bodies and how we can negate the bad stuff and make sure that the experience up there is good, but not so much up there is good, but also when they come back that they are not so damaged that they have a hard time returning to Earth. So it's a lot of different things involved there. But it affects not just the human body, it affects any animals you take up there, it affects any plants that you take up there, microorganisms, whatever. Microgravity affects everything because we are all evolved on the surface of planet Earth with a very strong gravitational pull. I mean, we call it an acceleration of gravity, 9.8 meters per second squared. I mean, that's really, we are used to that, and we thrive in that. Our muscles and our bones are strong because of that. You get up there and everything gets weird. So, what is microgravity? How is microgravity created? That's our two questions here. First off, for a definition of what is microgravity. Oh, I forgot. We got a couple of bad terms here. I'm sorry, I'm in your way here. I apologize. Next time I get in your way, you're going to reach over and whap me one? Okay? All right, thank you. There are a couple of bad terms, and these are terms that cause a lot of confusion out there. So if you can avoid these terms in the classroom, you are a whole better off. One of them is zero-G, and unfortunately NASA still can't quite get through their heads that zero-G is not a real term, because you'll hear astronauts talking about up in space and say zero-G. What they mean is not up in space where it is zero-G, up in space where it feels like it's zero-G. And I'll tell you why it's not zero-G. Not bad. Okay. Let's take the universal law of gravitation. Now, the universal law of gravitation was set up by Isaac Newton a long time ago, and that G right there was one of those little squiggly things that kind of go like this, which means sort of equal to, not proportional to. That's what he had. And then another scientist, Henry Cavendish, came along and actually figured out what the G is, the fudge factor that actually makes the equation work. Well, what Newton said was that the force of gravity is equal to a mass 1 times mass 2 over radius squared. Mass 1 refers to Earth. Mass 2 refers to, well, in this case, a ball sitting on the surface of Earth. So mass 1, mass 2. And I forgot the mass 1 label on there. One of these days I have to remember to put it back on there. And then finally, the radius is the distance from the center of mass of Earth, to the center of mass of that ball sitting on the surface of Earth. So when you think of radius, you're thinking about from the center of mass to the center of mass. Now, it could be you standing on Earth, and it'd be the center of your mass to the center of Earth, which is the center of mass of Earth. Okay, now that looks complicated, but it's not. It's really quite simple. So one thing you can say here is the bigger this mass is and the bigger that mass is, the stronger the force will be. Yeah, true. But even more important, though, is this r squared. That distance right there makes all the difference in the world, and I'll show you how. Here's the equation again, and let's put two balls side by side, and the radius, we're going to call it 1. It could be 1 foot, 1 centimeter, it doesn't matter what it is. We're just going to say it's 1, all right? And therefore, we're going to say, the force of gravity, we're going to call that 1. I'm not worried about units now. Just to give you an idea of the relationship is what we're doing here. Okay, let's double the distance. R equals 2. What is the force? Well, you look at that equation right there. Well, it's going to get better there except for one thing. Here's how the r comes in there. You double the radius here. Your force is then reduced by the square, so it's like having this number over 4. So the force is now 1/4 as great by doubling the distance. Let's double the distance again. Now the r is 4. See what's happening here? R is 8. So all we're doing is squaring that radius. And then we go to the last one I've got room for, R is 16, and the force is 1/256. Here's the important point, though. R can become infinitely large, I mean way out in the galaxy or the universe, but F will never, ever, ever become 0. That's the part that's most important about this whole idea here. It'll get extremely small, but it will never become 0. You can't have 0 gravity. That's the point about that. So 0 gravity is a bad term. So let's try another term, weightlessness. That's easier. Hey, get up there, you don't weigh anything. Well, nope, not really so. The reason you don't weigh anything up there is because there aren't any scales that are designed to work in microgravity, in orbit around Earth. If you had a scale that was designed to work up there, you could measure your weight. And wait, what's going on here? Let's see why. Well, here's what weight is. Weight is your mass times gravity. Now, let's face it. You go up there in space and in orbit around the Earth, and your mass doesn't suddenly change. Okay, so that's the same as it was when you lifted off. You know, gravity, well, it can never be 0. So how could you end up with a 0 number for weightlessness and make it weightless? So what you'll do if you want to use the term weightless is you talk about things like apparent weightlessness. And suddenly the vocabulary is getting weirder and weirder. Oh, yeah, up in space where you're apparently weightless. Like, huh? You know, everybody gets confused about that. So that's part of the problem with the terminology. Nobody has come up with a good word. If you could come up with a good word, you know, they would give you an award at the convention for scientists. You know, they'd all be happy with you. So nobody's happy about that. But still, we can't have weightlessness. So 0G, weightlessness, wrong. It's not possible. Okay. So then we're stuck with this word, microgravity. Microgravity is an environment where gravity's effects, make that important there, right? Gravity's effects are greatly reduced. That's my definition of microgravity. It's one that's pretty well accepted, although some scientists will talk about particular thresholds, like what the magnitude is, where the effects are, and then they argue over, you know, well, mine's has less effect than your threshold. You know, it's silly. But basically, when the effects are greatly reduced. And what would the effects be? Let's say you have a glob of water, you know, on Earth that forms a drop, hits the floor and all that kind of stuff. In microgravity, it forms a beautiful sphere. We saw that sphere the other day when I showed that optic presentation. So that shows an example of microgravity. That sphere was beautiful, and it just kind of hung there because they were in that microgravity environment where gravity's effects are greatly reduced. But here we get to the real point, how? And when you understand how, you begin to understand what it is. Okay, our first one here is distance. Now, that's hard to see there, but let's imagine that's the moon and that's the Earth right there, and we got a line between the two of them, okay? And if you were out as far as the moon, now I'm not saying you're standing on the moon because the moon has its own gravity, but let's say that you're over here, the same distance from the Earth as the moon is. The gravity that you would feel, the pull from Earth that you would feel, would be 1/3600th of a g. Now, we call this attenuation, basically. The farther away you get from something, the less you feel. But gravity doesn't go away. And this is a good way to reduce the gravity's effects on you. The only trouble is it's really hard to get that far away. And if you were to increase the distance to 17 times, so take it way out there, 17 times farther than the moon, well, the effect of gravity would be 1/1,000,000th of the gravity on the surface of Earth. So you're not getting rid of gravity, but you are reducing its effect by simply getting farther from the object that's pulling on you. But who can go 17 times farther away from the Earth, farther than the moon from Earth? We can't do. That's not practical. But it is one way to do it. All right. Well, here's another way. And this is the way that we deal with free fall. Free fall is a way to reduce gravity's effects. And I'm going to start off with a classic elevator. So we got a person in the elevator standing on a Toledo scale. You know, the scale is a lever-operated scale and so forth. Very accurate weight, honest weight. And so you can see the person's weight right here. The scale is stationary. The elevator car is stationary. Okay. So what we have with that is no motion, and on the scale you have your normal weight. But watch what happens when we change the elevator, get it moving. Let's say that we go down. Or rather go up, excuse me. We're going to go up. Upward acceleration. And what we have is the illusion of increased weight. Because your body has inertia, your body pushes on the scale goes up. Now, if you don't believe me, it's kind of hard to move a Toledo scale around, but take your bathroom scale to an elevator in a tall building. You may have to explain to the security guard what you're trying to do, but you set the scale down, and everybody's watching you, and of course it's the time, you know, you're letting people know what you weigh, and you stand in there, push that button, and that number will, that scale will go up, because your inertia is pushing down on it. When you hit the terminal speed of the elevator car, I mean, it goes as fast as it's going, it keeps climbing, then your weight goes back to what it was. So we can actually increase your weight momentarily by the upward acceleration. Okay, let's try another one. Now we're up top of the building. We're going to go down. Down we go. And when that happens, we have a downward acceleration. And if you watch the scale, the number goes down. You've lost weight. Or at least you've lost the feeling of weight, anyways, according to that. Again, your inertia puts a drag, kind of slows you down, and the scale drops off from under you. You depress it less than you did before, and the weight goes down, or at least the illusion of weight going down. Now we're at the top of the building, and this is like the new, what do they call that? They changed the name of the Sears Tower, but in one of the really, really big buildings, or the Willie Tower, yes, right. Willis, okay. The Willis Tower in Chicago, or the old Enron building here in Houston, really tall elevator, express elevator, and they haven't maintained it, especially in the Enron building, who knows. The cables break, and the elevator shoots down the shaft, falls down the shaft, and you're on board. Here's what happens. Ah! What you have here is a case of free fall, and you have the illusion of 0G, or weightlessness. But it's an illusion, because you know it's an illusion when you reach the bottom. Yeah. So that's an illusion. You really are falling, but it feels like you don't have any weight. Or it feels like you're in 0G. We call that microgravity. It's created by free fall. That's all we're saying here. If you're falling, it feels like you don't weigh anything. It feels like gravity's effects are gone. That's the whole point behind this. Now, the birthplace of microgravity in science and technology actually took place a long time ago. We didn't need rockets to figure this out. In 1783, a fellow by the name of William Watts in Bristol, England, made this building. Actually, he took an old existing building, put a tower on top of it, and then he melted lead, poured it through a sieve, and the lead dropped down the entire building into a pool of water. And when it got down there, by that time, the lead drops had formed perfect spheres, and they quenched, and they were ready to go. They made small shot. Now, when you were making, say you're during the Civil War or something, you're pouring your lead shot and so forth, you get it out of the mold, then you have to kind of trim it off, get anything sticking off of it, so the shot will fly. You have to do that. Well, he didn't have to do that with his shot, so he made perfect shot by simply letting it fall. So using this idea of microgravity, or we didn't call it that, of course, but the idea that it felt like there's no weight, the lead formed that sphere as it fell. Beautiful sphere. So the surface tension pulled it into a sphere, made a great shot, and then they would grade the size of the shot pieces and sell them for scatter guns and whatever else. So it was a good way to do that. And when that invention was made, they went around the world. People went around the world and built other towers. They look like big smokestacks. There's Tasmania, but if you've ever been to downtown Baltimore, you can still see this one standing there. This is the Phoenix Shot Tower, 71 meters tall, and they used to go up there with. I wouldn't want to be the person that had to haul the lead up to the top floor, but they'd haul the lead up there, melt it up there, pour it through, and then pull out the beautifully formed shot down here, and that is still available for you to see. That shot tower. There's one in the state of Wisconsin. Instead of that being a tower, what it is there's a cliff on the Wisconsin River, and they have a little building that kind of sticks out over the edge, and they melt the lead and they pour it through it, and it falls down, and then below there's kind of a step ledge. They actually mined through that and then mined out this way, so the thing would hit the pool of water, then they take it out the mine, and they put it onto a barge and float it down the river, and that was a big deal during the Civil War. It was actually making a lot of shot there for the various sides. There's another one. This tower here is located in Cleveland, Ohio at the NASA Glenn Flight Research Center. Now, this is a big one. This tower goes straight into the ground. I mean, you go to this laboratory, it looks like an ordinary building or industrial building. It goes 500 feet straight down into the ground. And you can you go to the lab and take a tour, then you look down this thing, you hang onto your glasses, and you look down there. It's like looking down a 500-foot smokestack. Down at the bottom is a little white thing, which is the target. The target is actually a basin filled with styrofoam beads like you'd find in a beanbag chair. Actually, it's about this big across when you see it, I mean, if you were down there. And they'll raise a package inside that thing to the very top. They put a cap over the top. They pump out all the air from this thing so that you don't have air resistance to really make the fall good. And then they do a countdown, and this payload, which is wholly on a cable right now. It's a cable, so there's the opening at the top, and they're hoisting it up there. That package will hit the basin, and generally speaking, the clearance is about that much on each side. And when they drop it, they have to aim it so that they counteract the rotation of Earth. In the 5 seconds, that basin has moved a bit, so they have to aim where it will be in the 5 seconds of the drop. And this is amazing. And the thing gets 5 seconds of free fall, and when it hits these bean bags, these little styrofoam beads, they're too hard. So they actually, the very last moment before it hits, they pump air through that to stir them up a bit to make them a little more puffy. And it goes, it's got a 35G deceleration, and then they pull it out, they study it. And on the way down, there's cameras and transmitters so they can monitor the entire thing during its fall. And here's a great one. They have also in here a catapult. And they place the package on the bottom floor, the basin's gone, and they shoot this thing up, which might weigh a ton. It'll fly straight up, miss the ceiling by about that much, fall back down, and by the time it falls back down, the basin has been moved back into place to catch it. Yeah, I mean, it's amazing. There are bigger ones in Japan and in Germany because they're using mine shafts there. And they've got one, I think, in Japan, or it may be Germany, I'm not sure which. It has a 10-second straight fall. I mean, that's really amazing. All right, now here's another way to do this, and this is the famous one. I bet you all know the nickname of this. The Vomit Comet, yeah, that's the nickname. And I can personally attest to the accuracy of that name. Oh, my God. Okay. What happens is they used to use a 707, and then they had a 707 was the most recent airplane. Now they're using the C-9D, which is, I don't know what it is about NASA. They have to change things around. That's a DC-9. But they call it C-9D. Just, I don't know, maybe they don't want you to know it's a DC-9. Anyhow, it's an airplane, commercial plane, right there it is. It's the same DC-9, a little smaller version. It's not one of those stretch ones that they use now, occasionally. But all the seats, almost all the seats, except for a few in the back, are removed. There's padding all through it. There's lighting put on there, power supplies, various support services along the way. And that is where you would fly if you're going to do an experiment. The thing about this is you don't want to be going to the Glenn Research Center and climb into that little payload thing and drop. You'll be killed by that. So instead, you can ride with your experiment on this plane. Now, the microgravity it produces is not quite as clean and good, but it still gives you a lot to work with. So you can understand about, say, you got an experiment you want to fly in space. You want to make sure it works before you fly it up there because it costs about $20,000 a pound to raise things to Earth orbit. You know, even though you may be flying on NASA's dollar, it's still very expensive. Let's verify it before we get up in space, so therefore we know it's going to work. All right. Anyhow. So, you get on this plane, it flies out over the Gulf of Mexico, It gets to about 24,000 feet. And everybody's sitting in the seats, and they tell you, okay, you can get out there, and you go to your experiment, you start doing stuff with it. Then the plane does this. The pilot pulls back on the yoke, and the plane shoots up. And at this point, you get 1.8 G because you're changing your direction. Your inertia pushes you into the floor. It's like doing roller coaster hills. That's what it amounts to. So you begin to climb. So you got a higher G right there. But then when you get up to about there, the plane is now kind of throws you up in the air, basically. So you get this high G, and then suddenly your body is being tossed up into the air. The plane is kind of now in a fall, actually a fall, because you can fall upward. I mean, if you take a baseball and you throw it in the air, it's in fall the entire time you let that ball go until it hits the ground. So it's falling upward, then it falls downward. So on the way up, the G-force drops to about 1/100th the force that you feel on the ground. So you begin to feel real light. Then you get to the top over the arc here, and this is a parabola shape, by the way. You get to the top, and then the force drops down to about 1,000th of a G. And the pilot kind of throws the yoke over so the plane kind of noses down. And then you hit that 100, then you hit the 1.8, and then you hit back to 1 like that. So it's really kind of a stressful thing. This takes about 25 seconds to go from here to there. And during that time period, your body goes from 1/8 to 1/100th, 1/1000th, 1/8, and back to 1. I mean, it's stressful. It's like riding a 40,000, an 8,000-foot roller coaster hill. Except that you do this maybe 40 times. And that can be very powerful, very provocative physical effects. Some people get on there and they could ride roller coasters all day long and never have a problem. Then there are people like myself that, oh, gee, first time I got on that plane there, I made it through, I think it was like 15 parabolas. And then out came the bag. And that bag stayed to my face for the next 25 parabolas. I just tried to find a place to get a hole here so I could breathe. I hung onto a cargo strap. We put them on the floor so you can hang on when you need to. And I'm hanging on there for dear life, holding the bag. And I'm not really able to vomit. I'm actually doing the dry heaves, which are worse. If I could have actually thrown up properly, I probably would have felt a whole lot better. But I couldn't. So I got the dry heaves. And finally, we come back to the airport. We land. And then you get off the plane. You're wearing coveralls. It's hot and so forth. And, Ellington Field. And then I got this bag here. I'm walking like this. I was so sick. I had the shakes. And it wasn't until I got back almost to home that made the final turn when the bag came out again. At that point, everything was fine. Oh, boy. It was big time getting sick. So, absolutely, if you feel like that, you never want to do it again. So the second time I got on the plane, I am a guy, I figured I'm going to take different pills this time. I'll be fine. Well, I got sick again, this time at like 10 parabolas. And again I had the dry heaves. And it was just terrible. So the third time, I know it sounds really stupid. The third time, I had another plan how I was going to be fine. And it was even worse, like 8 parabolas. I was sick again. This time I somehow crawled back to the seats in the back of the plane, strapped in. I had one of these little pocket fans and like this. It was really, I got so sick you have to die to get better. I mean, that's really how it goes. All of a sudden, about 25 parabolas into it, or 28 parabolas into the flight, one of the flight technicians come back and say, Greg, make sure you're properly we have to go back to the airport. We're having mechanical problems. So make sure you're tightly buckled in. So I'm thinking to myself, we're going to crash. Thank God. But then there are these other people that love it, and I'll tell you, if you're feeling sick and you're also miserable and you look up and you see some person squealing and having the greatest time flying over your head, that makes it even worse. Never open your eyes when you're sick on that plane. All right, well, a lot of people love it. And there is a plane now, a DC-9, that is flown by a corporation called Zero G. I'm sorry they use the term Zero G. They're using the historical term because it's been around for a long time. And you can get a ride on that plane if you have like $3,700, I think is the fare. But there are programs where they actually fund teachers. So if you get on their website, the Zero G Corporation, there are programs you can apply for where if you get selected, you get a free trip on there. And they do 15 parabolas. They do a couple of Mars parabolas, which means basically what you do, instead of making that really steep parabola, they make it a little flatter so you don't get quite as strong gravitational change, or the field of the change. You can simulate Martian gravity, then the parabola gets steeper, and you can simulate lunar gravity, and then finally they do the biggie, and you do the microgravity. There are other programs. There are programs like that out there, and another program that's out there I just heard about. They've already selected the people, but the space plane company out in California, the Scale Composite, they've selected 7 educators to be the first teachers to fly into space using their plane and return to the classroom, which has been kind of an irritating thing about, oh, we're going to fly teachers in space and they're never going to see kids again, like something. Well, okay. But it's sort of the way it works out, that they change their career to become astronauts and they don't get back in the classroom as teachers. So this is a program that will have it. There's a teacher in Killeen, Texas, actually a principal of a school there. Westward Elementary has been one of the 7. So that's really exciting. Okay, here's what happens on the plane. That's a water balloon, and they're in microgravity. And, of course, when they pull out the parabola, they've got to catch that water as best they can. They got a little overly exuberant in this one. That one made quite a mess. But you notice how they put plastic all over the place, and that was trying to capture the water there. That's the kind of stuff that happens there. But all that happens, it looks like there's no gravity. It's all because they're falling, and the drops are falling. The plane is kind of falling through the sky, too. Everything's falling together, and that produces this effect as though gravity had gone away. Here's another way to do it. You can do it on a sounding rocket, although you're not riding this one. The sounding rocket won't get you back alive, but it really puts high G-force on the liftoff. And what you have here is this really steep path. As the rocket goes up there, through there it coasts in this arch right there, and you can get several minutes of microgravity before it comes back down, then parachute recovery. That's a good way to do it. But here's the way that Isaac Newton came up with, not using this particular equipment, but Isaac Newton came up with a really great idea. Among his many, many achievements, he came up with the idea of how you could put a satellite around the Earth. So this is over 300 years ago he figured this out. And what he imagined was you got a big mountain that goes so high it's above the atmosphere of Earth, so you don't have to worry about friction with the air. And you got a cannon there, and you fire the cannon using black powder, and the cannonball shoots out. Now we know, because you throw things, if you throw something off, it's going to fall in a curved path because you have that forward motion and you have the downward pull of gravity. So it causes things to curve. Good. Okay. Let's fire a cannonball here with not too much black powder and see what happens. Bang, right there. Fire it again, this time more black powder. It goes farther. Bang, again. When you get the right amount of black powder, you'll notice how the path here changes each time, and it becomes more shaped like the shape of Earth. When the path finally becomes a circle, the cannonball comes back to where it was, and that is an orbit. That's the idea behind it. Of course, we don't launch rockets with cannons, although Jules Verne used that idea for his trip to the moon. He actually had a big cannon that would launch from Florida using a spacecraft called the Columbiad, and it was about the same size as the Columbia space capsule launched from Florida that actually went to the moon. I don't know if they named it Columbia because it sounded like Verne saying or not, but regardless, you don't use cannons. What you do is you use a rocket, the rocket lifts off, and you don't see it too well. It looks like it's going straight up in the sky. It's not really. What it does is immediately starts to arc over and begin to follow in the direction you want it to go, the orbit that you're looking for. And in no time at all, the rocket is literally going horizontal. Now, as it's going horizontal, it couldn't stay in orbit there except for one thing. It keeps accelerating faster and faster. And as the more it accelerates, the higher the rocket goes. So if you can imagine yourself like having a ball on a string and you kind of twirl around slowly, you get that centrifugal acceleration, you're kind of pulling the ball outward. And if you spin it faster, it pulls harder. Well, the faster you make it go, the more that rocket tries to go out and go away from Earth. When you finally hit the 17,600 mile orbital speed at 100 miles above, you can coordinate those two. You're 100 miles above Earth, traveling that fast. You can stay in orbit. That's how they do it. So they don't go up straight. They don't fly straight up like this and then make a right turn and go like that. They go like this and climb up there. Okay. When you have an orbit, that's where fun things happen, because the spacecraft stops firing its rocket engines and it just coasts. And it literally falls and falls. All the time it's falling towards Earth, but because of its forward motion, it's moving too fast, it misses Earth. That's the trick behind it. So what that does is it produces your microgravity effect. That's what it does. And here comes the big question. Why should I care? Big deal. Well, there are a lot of good reasons for it. Traditionally, scientists control for many things. When they do experiments and they try to do research, they control for things like temperature and pressure and composition, chemical composition, radiation across the entire electromagnetic spectrum. Depends on what you're doing, of course, what kind of experiment you have. Electric currents, magnetic fields. You can control all these things. These are good old laboratory controls, and you talk about that with your kids when you do experiments, controlling your experiment, making sure that your variables are the same except for the experimental variable that you're trying to figure out. But now, and also they have been able to do this too. They can create high G in two different ways. One way is the momentary high G, and it's an old picture here. That is the spacecraft called the Sonic Wind. And the Sonic Wind is on display in Alamogordo, New Mexico at the museum there. The person sitting on there is Colonel Paul Stapp. He was the investigator for these experiments, and he wouldn't let anybody get on that but himself. He didn't want to have to feel guilty about losing somebody's life, so he tested himself on there. And that thing used rockets. It shot along this long track, and then it had a tank of water in the other end to kind of hit the water tank and slow it down. Well, that's what he looked like at 35 Gs. It was amazing to do that. He lived to be like 85. I don't know what kind of medical problems he may have had, but I mean, when they stopped that thing, he'd have to really hold his eyelids shut because his eyeballs were going to try to pop out, and he kind of looked like sort of Popeye for a while there until everything resettled. It was an amazing set of experiments, but he found that you could handle those high G forces. Then you have sustained high G, which would be things like centrifuges, and it used to be. In fact, I think they still do it. There's the Air Force, I think, has a centrifuge somewhere here in Texas, I think it's in Texas. I'm not sure where it is. Anyways, you get on a thing and you experience those high Gs because you're going to be a fighter pilot. If the minute you get into high G, you say, let me out of here, you're not a good Top Gun type candidate. So you got to know about those things. All right. Until the space age, creating low G, or microgravity, was only possible for very brief periods. We're talking dropping things for short distances. But with the space age, because now we can go into orbit, we can make things happen for long periods of time. Instead of seconds or minutes, using the space shuttle or the new vehicles that are coming along, we can go for days or weeks, and with the International Space Station, we can do it for months or years. And now we have a chance to do some really basic research using gravity as a variable. You do one experiment on the ground, you do the same experiment up there, and you let it run for a long time, and you can see all kinds of stuff. For example, what are some of the effects on things? Here's a candle flame, normal Earth candle flame. Now, you know with candle flames how they work basically. Candle flames are really classic things, and if you could do them in your classroom, just have the kids study, there's so much you can learn from these things. In fact, Michael Faraday wrote an entire school book on candle flame, and it's a classic, one of the classic science books. Well, with a candle flame, it looks like that in one gravity. In microgravity, it looks like this. Very, very different. Here's what's happening. In one gravity, you've got fresh air carrying oxygen in particular to the candle flame. You've got hot air currents, and the hot air currents cause the flame to stretch out and rise up, and that causes a low pressure zone in here. More air comes in, is drawn in, heats up, away it goes. And it keeps the flame refreshed and gives you that beautiful candle flame shape. So you've got strong convection currents bring in oxygen, carry away combustion products. But in microgravity, you don't have those convection currents because there really is no up or down. When the things get hot, where's the hot stuff going to go? It's not going to rise because gravity's effects are gone by microgravity. So it stays there. And you end up with something like this, and it's hard to see those arrows, but we have instead the process of diffusion. Oxygen just gradually works its way in, and the bad stuff works its way out. But it makes a nice spherical flame. You know, diffusion is that thing that happens in the classroom where some girl in the back of the room opens up a bottle of perfume to touch up a little bit, and then suddenly everybody goes, and it works its way through the entire room. That's what we're talking about, that diffusion. So diffusion currents exchange the oxygen. It's a very inefficient process. The flame is that dull level. It's hard to even see it unless you're using a camera and you're really intensifying the light gathering of the camera. These are drops of water on a piece of wax paper. If you want to show how surface tension makes drops appear to be round, just put wax paper down. It's like having a wax car. wax paper down, put some drops of water on there, and the big drops tend to be flatter than the small drops, which became almost spherical because of surface tension. But still, the bigger that drop becomes, if those two were to combine, everything really starts to flatten out. That's what happens on Earth. So you got your 1 GeV water drops here, and they are flattened out somewhat by gravity. In microgravity, and this drop is being heated, so it's forming bubbles, and the drop, actually, I think the drop may be spinning, but the bubbles stay right there where they are. There's no reason for them to rise. And you can make drops that are quite large. Now, they don't encourage you to make really big drops on the space station, because what if it gets away from you, you bump it or something, or somebody blows on it or whatever. You don't want water flying all around all your electronic stuff. It would be bad. So whenever they do those drop experiments, they have towels out there, and they're all ready to go, and they keep them about this size here for convenience sake. And then when they're finished with them, they do one of two things. They'll kind of sneak up to the drop and go and drink it, and it all just comes right in, except for the stuff that ends up in your face, which is good for a laugh line. Or they'll just take a towel and just kind of touch it with a towel, and it just capillary action pulls it right into the towel, and then the towel goes in, the trash receptacle, essentially. They get rid of it because it's now no longer useful for other things. Okay. Because the bubbles stay put, we can say that there is no such thing as buoyancy or sedimentation. And that has to do with chemical experiments. If you were to make a chemical experiment on the Earth, and so you got this little beaker right here, and you put down the beaker, and you got water in there, and I'm going to pour in this, and I'm going to pour in that. Some stuff will settle right to the bottom. Some stuff will stay at the top, and so forth. You stir it, do whatever you want. In space, wherever you put it, like if you were to take a beaker, if you could have a beaker of water, and you had steel shot, and you kind of put it in the water, it would stay at the surface. It would stay right, it wouldn't have any reason to fall. So then you have to use stirring to get it down there, and wherever it is, halfway down, it'll stay there. It won't just drop into the bottom. That's the thing about that. So there's different laboratory procedures involved in doing these things. Now, these are protein crystals, and protein crystals and virus crystals. They are very important to us. If we look at the human body, I don't know what the number is. Every source I go to that is very authoritative has a different number for this, but somewhere between 150,000 to 300,000 proteins are found in the normal human body. All these different things have functions and so forth. They're amazing chemicals. They do stuff. And they have extremely complex molecules that tend to be ribbon shape, and they're all over the place. The trouble is when you try to grow a protein crystal on the ground to figure out what it's like, what it is, in the crystal vat itself, the protein crystal will tend to be kind of sag because of gravity. And it may fold up on itself and do all kinds of weird things. And you end up with a protein crystal that's been distorted. You grow the same crystal up in space, and the crystal the molecules take their proper shape, the shape they're supposed to have. And you can actually create very, very pure crystals. You don't make gigantic monsters. You just make very little ones, but they're very, very pure. You bring them back, use X-ray crystallography to analyze their structure, because now you know what the structure is, because that's really the good example. Then you can start doing your playing around, like moving this one atom, that atom, and so forth, replacing, changing the structure, maybe to make it a trigger for some sort of new medicine. Could maybe make it a trigger to block some medical condition. So you have a chance to do really good medical research on that, looking for various drugs and so on. Here's another one, though. What does it do to you? And what it does to you is very interesting at first. That's Dan Brandenstein. He, on the left, is on Earth. And then, like those typical ads, for weight loss, where the girl is standing there and she's looking like this. And then the next shot, when she's lost the weight, she's feeling, really looks beautiful. Well, sort of like he's got the reverse here. Now in space, he's not smiling. But you can still get an idea that there is a change. Look at that. His face is puffy. I mean, it's really looking puffy there. And what has happened is that there's been a fluid shift. He gets up into microgravity, there's a fluid shift, and some of the fluid in his body moves upward. It's not a lot of fluid, but it's enough to change his facial appearance. We have very complex and wonderful bodies, and our heart pumps the blood through the bodies and so forth. When the blood gets down to the feet, it could easily stay there because gravity, to get it back up takes a lot of effort. So in our legs and the veins, the big veins coming up from the legs, there are what we might call secondary pumps, but basically they're valves. So the blood gets down there, and it can next to the dunk, and the blood moves up a bit, and the leg vessels, the veins actually kind of close down a little bit and kind of help the blood stay there. So each time it pulls up some more and it holds it and holds it. It's kind of like the old hand-operated water pumps. You know, you kind of grab it, bring it up a little bit, then bring it up a bit more and so forth, and never let it fall back down. It's like those old hand pumps. Well, our bodies work that way. Well, nothing tells the legs to stop doing that when you get in space. So they kind of squeeze things off a bit, and the fluid comes up here, and gravity is not helping the fluid to go back down. So your feet tend to be a bit cold. Your legs thin out. They call that bird legs, because your legs do look a whole lot skinnier than they did before. And your face starts to puff out. You feel kind of congested, sinusy, you know, your head's kind of foggy. That doesn't last forever because you have various sensors at the baroreceptors that kind of look at your blood pressure and so on, and they think, gee, there's a lot of extra fluid up here. It's time to eliminate some blood. So some of the blood in your blood supply is then converted to urine, you know, eventually to urine, and you pass it out. And now you have less blood in space than you had when you were on Earth. Not bad. It's okay. It really is, because that's normal. You got as much as you need up there. Trouble is when you come back to Earth, suddenly you are short of blood. And this is why when the astronauts land, you don't see them come dashing out the door of the spacecraft, I'm glad, kissing the ground. They don't do that. They sit inside for a good hour or so. They're drinking fluids, and they're trying to get themselves back to normal, trying to rebuild their fluid supply. And in really extreme cases, they could even get some intravenous if they're really, really sick and so forth. Then they come down, and they still come down kind of holding the ladder and smiling and trying to, you know, grabbing the ladder. And there have been cases, I think it was Heidi Marie Piper or something or another. I forgot her last name, married name now. She was in a post-flight press conference and said, oh, we're so glad to be home, and poof, down she went. You got to believe that she hears about that all the time. But it's a normal thing. You know, that just happened to be on camera. Other astronauts have passed out. But no astronaut wants to do the old tumble down the stairs routine. You know, they don't want to do that. But that's what happens there. There's so many effects with microgravity. It's absolutely wonderful. Plants. When you got plants up there, they're different too. That's a really great picture with a drop of water, a bubble inside, and it's in a little plant, I think a pea pod or some sort. Plants will grow very nicely in space, except they sometimes have trouble figuring out which way to grow. Of course, if you have a lighting system inside your chamber for plants, they'll grow towards the light. That's what they do. But the roots may or may not stay in the soil or the planting medium. Sometimes they come out too. And if you have, so you have to design it so that you've got a system where the medium is wetter down at the bottom, so the roots are trying to work their way towards the water. They want to stay with the water. If the medium is sort of dryish or whatever, they go anywhere they want to. Just so many things here. Well, I think that was the last slide there. Except if you want more information, there is a full curriculum guide called Microgravity. And by chance, I'm one of the authors of this guide. It's on the CD. It's a PDF file. I put it on there for you. It's a big guide. It's a lot bigger than you probably want, but there's a bunch of activities. Read the first 5 or 10 pages. Skip all the stuff in the middle, because that's the scientist. Every scientist that flew in microgravity or flew their experiment wanted their experiment featured, so that was a political thing. And then you can go to the activities in the back end. All right, that's our microgravity presentation.